So welcome back. Um, so in the second half, I'm going to talk you through in good detail regarding this beat slicing patch. So what we have then is a basic implementation where we essentially play back the slices using a list. Okay, so that's the main thing here. So what we're looking at are three lists, and you see the first list, it's just numbers incrementing by 1. So this one should play back the actual loaded sound unaltered. And you've guessed it, what we're doing is we're cutting it up into 16 bits. So regardless of what it contains musically, we are going to consider 16 different bits. Now, the way this is done is that the buffer is loaded with the file, but there is no cutting really going on as far as that buffer is concerned. What's happening is that we have a clever way of playing it back. So it actually becomes the pattern of how we play back the file. So that's all stored in the jumps table. With the $0, it's helpful once this patch becomes a module. So it has its own table internally. But actually, in this current state, it is just a standalone, really. So you could omit the $0 altogether. So that's this table. It's defined here. And typically, when we send a list to the table loads all the elements in the list. Okay, so the jumps is the table that contains the number. So as we will play back, we will be reading through these numbers, really. Okay, we'll come to that. Let's discuss the loading of the sample. Maybe that's a fairly straightforward thing. You've seen something similar. I mean, this is kind of meant to be used with loading 1 bar of a 4/4 beat, and then you get the 16ths cut up. But as I said, you could come up with a variety of ways of abusing this. And indeed, this is a kind of a really bare bones simplified implementation that I'm showing you just to make sure that you understand the insides, which will allow you to do something interesting potentially. So loading a bar, open panel, and then we pack that with the symbol. Again, this is a mechanism which is slightly more advanced than needed here, because it will also make sure that if you use this as a module, if you load this patch multiple times, that each one will internally have a different buffer. Okay. So essentially we have these two, right? We have the jumps and just the BB. And the BB will contain the sound. Okay, so that's reading of the buffer. So you get the file name from the open panel. To that you add into the list this other symbol, which will be the buffer name. And then a read message to the sound filer, which will display it up here with the resize, so it actually fits in fully. Let's see, I should be able to load another sample here as well. Here we go. There's quite a few things. Funky 1 bar. There we go. So at that stage, the sound filer would send through the duration of this loaded sample, and the duration expressed in samples. Okay, so there is 108,000 samples. So at 44K, that's just above 2 seconds. Okay, so that's my loading mechanism. And then we will come to how this value will be needed. So now comes the big chunk here. How does this playback thing actually work? Now, maybe the best thing is to start from the core of it, which is the phaser. Okay, so the core operation is that we have a phaser which goes up gradually, linearly, from one value to the next. And in doing that, it may read a buffer, which essentially means playing back the buffer. And when it comes to the end, when the phaser drops, then the reading actually comes back to the beginning of the sample. So actually what we have then is that the buffer reading mechanism, right? It receives values that come from the phaser. What happens in between is that they're being scaled. Okay, so the phaser gives us a range of 0 to 1. But in order to read multiple samples, we actually have to go much higher than that, because each next integer will load in or play back the very next sample. So that's why we actually multiply here the phaser with the duration in samples. So what this makes sure is that this phaser becomes locked into the duration of the buffer. Okay, so when the phaser reaches the maximum, then we reach the end of the buffer, right? So this phaser, after this multiplication, in this case, will run between 0 and 100,000. That's what happens as we multiply it. Okay, so actually, no matter the playback speed of the phaser, which is something we will control with the frequency of the phaser, regardless of that playback speed, the phaser is always locked to go from the beginning to the end of the sample. Okay. So we can actually explore that already, because this phaser mechanism, because it's locked in, it will actually play back on its own. Okay, you don't really need the complex slice reading mechanism in order to get the loop back. Okay, so if I have the metronome, which is responsible for reading the stuff. I have it off now. So what I'll do, I'll just hack in a playback frequency. Okay. So this is my loop. It is being played back slightly slower, but you hear that it is well cut, so to speak. It plays back in the loop. So this happens without any of the metronome-based slicing. Okay, so I have a little 0 here to stop that. So I can actually hack it here already. And as you've heard, I can get a different playback speed of the loop. Now, part of the exercises we will do, we will try to open this one up and add a few things. So part of the workshop will go into making a switch here, right? So currently this is just a hack, but I might as well have a switch between following the playback speed of the actual file or following the playback speed based on the slice reading mechanism and the BPM thereof. Okay. So we could figure out what needs to be the frequency of the phaser for this duration of the file such that it plays back original speed. Okay, so just roughly, we will deal with this in more detail, but we said roughly it is a bit more than 2 seconds. Okay, so if it was 2 seconds, then we would need a half hertz oscillator phaser to actually have a period which takes 2 seconds. So in order to play back the original speed, in this case, we would need a phaser running at about 0.4 hertz, just guessing it, slightly more than 0.325. You probably heard it recognized it as being slightly slower than it's likely to be as the original. Okay, but we will leave that for exercise. As I said, the focus here now is to actually feel comfortable with this patch, to have a little bit of a cathartic, yes, I understand what it does and how it does it. Okay, so now we can start here from the top, or continue, I should say. So basic on-off button, which controls the metronome. Okay, so once the metronome kicks in, we will have the slice reading, this more complex list-based slice reading engaged. But let's first look at how we calculate the time interval for the metronome based on beats per minute control. Excuse me, yes? Oh, shit, the door is closed. Hello? Yes, I'm busy now, thank you. Slight interruption, you shall excuse me. Okay, so let's look at how how the metronome time interval is calculated from the BPM. So first of all, it's a bit of a brain work here, but essentially what we're doing is we're figuring the fact that beats per minute, if we have this amount of beats per minute, we will have 60 times that many, 1/60th of those beats per second. Okay, because a second is a 60th of a minute. If this is, let's take something simple. Well, it's playing already because it's changing this frequency, which is kind of unintended. So if we have a 60 beat per minute, that will actually give us 1 beat per second. Okay, but here what we're trying to get is the duration of 1 bar. Okay, so we further have 4 beats in a bar. Right, so that's why we have the 240 here. We actually have 60 times 4. We divide by that and then we take the reciprocal to get the duration, right? So from frequency, something per time interval, 1 over that will relate to the frequency. Okay, so that's fairly straightforward. If we have 60 beats per minute, right, we have 1 beat per second. So 1 bar takes 4 seconds. Okay, so that's duration of 1 bar, and then I can also test it. I mean, if I increase the BPM, then what I have is that the duration of 1 bar decreases. Right, makes sense. It becomes faster, so duration is smaller. Okay, and then from this duration of 1 bar, if I divide that duration by 16, then I get the duration of 1/16th note. Okay, so you see I could have skipped a step here or 2, but never mind, it is potentially more transparent like this. So then I get the duration of a 16th note, and then I get, by multiplying with 1,000, I can get the actual duration of a 16th note in milliseconds. Okay, so metronome responds to milliseconds. So what this will give me, it will give me a bang for every 16th note. Okay, so that's the bit of math around here, and the other task in the workshop will be to optimize this. So once you understand it by going through the steps, essentially what we have here is 1 division, another division, another division, and a multiplier. So we will see how this can be optimized. Okay, so from BPM we get to the duration of a 16th note, and then these bangs will go into the counter. Now this counter is fixed at 16, so it goes through all the bits. I hope we will get to make some 7/8 beats and other odd meters in the workshop as well. I will do my best. So actually once this starts running, you will see the increment here for every 16th note. Okay, so here we will get numbers 1 to 16 for every 16th note. And then we subtract 1. And this is in order to read from the table, because the table reading starts at 0. So after this point, we get 0 to 15. And what we do is we read from the jumps table. Okay. And then what we get out of the tab read will be the set of values which are stored in the lists up here in the right corner. So if we are using the first list, then essentially the number coming into the tab read will be the same as the number going out, right? So that will play back the sample through. And then as we mutate, change the numbers in the list, throw them around, we are able to play back a different slice, or any slice, any of the 16 slices at any of the 16 points in time. Okay. So then we see that as the position to read as an integer, which is straightforward. And then we divide by 16 in order to scale that down to the range 0 to 1. Okay, so then below that, after division by 16, you get the fraction of the bar to read. Okay, so halfway, when you get halfway the bar, this will read 0.5, right? And it terminates at 1. Okay, so then comes the last bit, which is hopefully something you can appreciate. It is actually fairly straightforward. The thing to understand is how the phase input of the phaser works, right? So the phase input, whenever it receives a value, it will immediately jump to that value. So the phaser keeps running at the speed which is controlled by the frequency. Okay, but as soon as I send it a value between 0 and 1, it will jump to that phase of itself. So actually, because that's in the end multiplied by the duration in samples, it will jump to the position in the sample based on this fraction. Okay, so you see that actually this is a message chord. So it means that only when the metro bangs, then the calculation happens. We read from the list, or actually from the table that is populated by the list. And at that point in time, the phaser jumps and then keeps running at the exact same pace. Okay, so that's how this jumping is being done. Okay, and then potentially the final thing to understand here is that the phaser needs to run, if we are doing the slicing, the phaser needs to run at the frequency of one whole bar. Okay, so that's why if I have a 77 BPM, okay, it will read 0.32. So we can again go with a simpler value just to make sure. So if I have, if I have a 60 in here, that's kind of nice and simple. If I have a 60 there, then what I have is 1 beat per second, but 1 bar is 4 seconds. And therefore the frequency of each bar is 0.25, right? So we get only 1/4 of a bar per second. Okay, so that really is that. So the last thing maybe to explain here is, as I said, the reason why this plays back without the slicing being used is just because this phaser is locked to the duration of the sample, and if you set the frequency for the phaser, it will just do its thing. Okay? Now in this case, this is not actually the BPM. For this to be the BPM, I need to run the slicer. In fact, I said that wrong. It is the BPM. It is the exact same speed. But now I actually have the slicer running, right? So you actually see this one is incrementing 1 to 16, and this is my position read. Okay? So what I can do then is I can run this list, which is slightly different. What I can do is I can try to make a list which makes it really evident what's going on. Let's try to do that. So I will make a list which, let's say, repeats the first 2/16 twice, then goes into 2, 3, 2, 3, then goes 0, 1, 2, 3, 0, 1, 2, 3. Okay, so now I'm actually slicing up only the first 4/16 in this fashion. Let's verify that that works. Okay, so you see it's only the first quarter of the bar being looped. It's not directly looped. This second part is an actual loop. In the first part, I actually have even shorter loops, which then exist. I mean, evidently I can try to have some fun with this. Number 4 will be a snare drum, so I can place that strategically here halfway. Okay, I can also let's involve another snare drum in here. So let's put one here, and I would think that number 8 might be a snare drum as well. Let's see what 8, 9 would add in here. So you see, number 9 is my ghost note, so I can use that strategically. Let's put it here and there. Okay, so now, as I said, it was actually part of the whole aesthetic, the fact that the playback mechanism is different from the file, the resource organization. So what I can do now is I can just load in a different beat, and so this would be the original. Let's speed it up a bit. And I can slice it up in the same way that I did the previous one. Okay, so evidently number 9 was not the ghost note in this beat, but that should be fair. Okay, so you hear the phaser clicking here because now I've made this frequency of the phaser 0, so it never moves, but it's still jumping. And it might be encountering a different sample value for each jump, so you hear it ticking along with the 16ths. If I stop the metronome, that should stop as well. Okay, so that's that. I suggest you make sure that you fully understand this before the workshop, because we will start in the workshop with immediately manipulating it according to different tasks, few of them that I have mentioned already. So I'll see you later.